Hello, hello Nadir. I thought we'll continue into Equilibria. Like there are a bunch of things remaining, but I thought um, we'll finish Equilibrium and reaction kinetics so that we are done with like majority of the things, and then we can cover the rest organic and like these are just I guess we can discuss it in person together. I think these two chapters. So I'm hoping to finish everything by the end of this week. Uh, at least these ones, and then the other two you can at least start on your own and we can discuss it once. Yeah. Okay. Let's get started with equilibria. This, even though I marked it as yellow, I don't remember discussing it, so I'll treat it as if we have not discussed it before and then kind of take it from there again. But this is something that can maybe get confusing and it's a little bit of a tricky chapter. So make sure you understand things the way that they are supposed to be understood. And the best way again to do that is to read the book, do the problems, right? Like that, there's no shortcut, there's no formulas, there's no this thing, except like there are formulas, but in the sense they all come from logic and um, or some strong theoretical basis. So make sure you get that. Okay, that said, let's get started. So the chapter that we are going to see is equilibrium, right? So equilibrium, if you remember a little bit about equilibrium is what we call like dynamic, right? Like in the sense a goes to b but b also goes to a, right? Like so a is converting into b constantly and b is on constantly converting into a, but the rate at which a goes to b is the same as the rate at which b goes to a, which is why you don't see a change in a or b, right, at equilibrium, right? Initially, of course, if you remember, we used to draw graphs like this, right? Like like say there's a high and that decreases low, and then maybe like b starts at a lower value, but then it also kind of reaches at this point. You say equilibrium is reached because a has flattened out and b quantity has also flattened out. They don't have to be same. The idea is they should stop changing. So the idea is how much b becomes a and how much a becomes b makes these quantities happen, right? That is the final equilibrium quantity. So which is why we call dynamic. Like it's not that processes stopped happening. It's not that in a normal reaction, right? How we say A has converted to B. So and all of A is over, then the reaction stops. Something like titration, right? Like you add things into that pipette and things are over. And then the reaction stops. It's not like that in equilibrium. The reaction is always constantly happening, like throughout. Right? So that's what we say is a dynamic equilibrium. And equilibrium is always in a way dynamic. Okay, so with that short this thing, what we are going to talk about in this chapter mostly, and we are going to build up on is the idea of conjugate acids and bases, right? The idea in, if you remember, like the Bronsted-Lowry. Let me look at the spelling of Lowry. Bronsted-Lowry, Lowry. So Bronsted-Lowry theory of acid base says that acid is anything that gives H plus and base is anything that can take in the H plus, right? Or OH minus, or like take in that H plus. So this gives that H plus, or this takes in, this gives OH minus, or another way to say that is it takes um, H plus. So the acid that gives H plus, so an example would be something like NaOH, right? Like an example, so this becomes Cl minus, like in the sense the H plus has gone from here, right? And it has gone and attacked this guy, right? So this way, this is acting like an HCl is acting like an acid because it is giving off H plus, right? Like if we just write it like this, it gives off H plus, so it is an acid in a way, right? So from this, so this is what we call an acid, and this, so we get an H plus here. So what is left is called a conjugate base. So the idea is the reason why it's called a base is because this, like think of it this as an equilibrium, right? Like think of HCl converting into H plus and Cl minus. So it is giving off H plus. So to getting converted into Cl minus, but Cl minus itself can accept H plus. and then become HCl back. Like if you imagine this as an equilibrium, right? So this acts like a base because it can accept that H plus or taker or acceptor, right? So this is why it's called a base, and the reason why we call it a conjugate base is because it's like the conjugate base of this acid in a way. Like acid has conjugate base and base has conjugate acid, so to speak. We'll see an example of that as well. But this is the idea, right? So this is the acid, and then this is the corresponding conjugate base. If you have a different acid, then you'll have a different conjugate base. So if you have say H2SO4, then it gives a one this thing, and you're left with HSO4 minus, right? This is now the conjugate base, and this is the acid, right? Like it is always the thing that's left. So the idea is it can take the H plus and then go drive the reaction in reverse, right? Okay. We have studied equilibrium a little bit in 11th standard, so make sure you kind of revise those concepts as well. Okay. A thing like this would be a conjugate base because in this case NH3 plus H2O. So here H2O is giving away H plus and this is accepting that H plus, right? So this is acting like a base and this is the conjugate acid correspondingly, right? So this is the acid, this is the base, and you can call, like you can either call it this, you can call it NH3 can be the base, and that can be the conjugate acid, or it can be the other way also. There is the acid and this is the conjugate. So together we call it the conjugate pair, so to speak, right? Whenever you see an S3O plus, that you can see, you can think of this as H plus and H2O. So in a way, H2O can get cancelled, and this is the same equation as what we saw earlier. What I mean is that hydronium ion, like HCl plus H2O, this H plus comes from here and attacks this one, right? Forms H3O plus and Cl minus. So this is the conjugate base and this is the acid, of course. Right? The same equation in a way you can write this as HCl and H plus and Cl minus. Like I'm instead of this writing this as this and this is H plus plus H2O plus in a way, this guy. So this you can always, like, I kind of just remember this fact. Okay, once you understand that, then yeah, these are the things. Make sure you go through the book to understand things. Okay, so that is one thing. Next thing you need to understand is what we call Kw, or the ionic product of water. So this is an important idea. So ionic product of water is called Kw. So that's something that's always constant, right? Like, so what is Kw? Kw is H2O, like, which is the water in like liquid form, can split into H plus and OH minus ions, right? Like it can split inside like water. You can say that there are like H2O molecules and then there are H plus and OH minus in the same liquid, right? So we want to understand how can they split. So this is also an equilibrium. So if you were to say write what we write something like this, right? The Kc of the equation, right? Generally, so we write concentration of H plus, concentration of products, like the square brackets mean concentration, divided by H2O. Now the concentration of a liquid is always, we say, is a constant, so kind of we absorb that to the right hand side, like just don't bother about that. But like both of these are aqueous, right? Like inside water in a way. Like it's weird we calling it inside water, but like the idea is these are H plus ions, right? On this side you have molecules, right? So you want to look at ion concentration. So this product is what we call Kw, the concentration of H plus into concentration of OH minus. And what we know is Kw for water is always equal to 10 power minus 14 all the time. Okay, so it can happen that there are more H plus due to external sources, right? Like you can always add source of H plus, right, inside this. Say you add as some acid inside, right? Acid gives H plus. So if that gives H plus, then what happens is because this is constant H plus and OH minus, so this one rises a lot, right? Because of the external source. Because the product of this and this is constant, so this will reduce, right? This will have uh, important implications later, but the idea that you need to remember is this is called the ionic product of water, Kw, or K of water. and that's always a constant. So, and why is that specific number 10 power minus 14? That we will also see in a bit. Okay. Okay. So then we do the short calculation. That looks something like this. So if say there is only a water inside this solution, right? Like we said that you can add things externally, but we are saying there is nothing external. There is only water inside, right? So water, can split like H plus and OH minus, right? And you know that Kw is constant, which is this into this, which is 10 power minus 14, right? So if the only way that you can generate an H plus is through this reaction, not externally, then that means H plus and OH minus will have to be same, because every time you create an H plus, you create an OH minus, right? Because this is the only source of this reaction, right? If that is true, then in that case you can put this in back in the equation. So you get H plus square is 10 power minus 14, and that gives you H plus is 10 power minus 7. Right, so you have gotten the concentration of H plus, which can exist in a way naturally if there is nothing that's added to this. If there is acid or something that's added to it, or base that's added to it, then this concentration of H plus changes. But for now, it is half of this. Again, we'll see why this number is important. Okay, that part is important is coming now. So this is important in what we call the pH calculation. So this is, of course, you have heard this before. So pH is basically always this guy minus log base 10 of concentration H plus, whatever the concentration H plus. So if say in this pure water example that we saw, right, that H plus concentration was 10 power minus 7. So if you were to calculate pH of this, which is minus log of concentration of H plus, which is 10 power minus 7 in this case, right, 10 base 10, the base comes out, so minus of minus 7 into log 10 10, right, log 10 10 is 1, and this minus minus becomes plus, so you just get 7. So this is where this like famous thing that comes from, that neutral water, right, which is not acidic or basic, has a pH of 7, right? Now say if you were had an acidic solution, the acidic solution, since they have a lot of H plus, right? So say the concentration of H plus rose up to 10 power minus 2, say, right? Like understand that this is bigger than this, like this 10 power minus 7 is 0.000000, and then 1, and this is 10 power 02 is 0.01, which is of course bigger, right? So if say this is the concentration of H plus, then pH in this case will, you can go through the calculation, will be 2. So of course this is where it comes from, that if it is less than 7, then we call it acidic, right, like this is where the convention comes from. And base, of course, can go from 7 to 14 similarly, right? Like, so you can always calculate from ionic product what will be the corresponding concentration of OH minus. So if say bases produce OH minus, right? So bases raises the OH minus concentration to a very high level, right? Like, so this is high. Baseline we saw was 10 power minus 7, right? Again, this has risen. So correspondingly, you can calculate the H plus concentration. It will be 10 power minus 14 divided by minus 2, because the product of that is constant, right? Which is this guy. So you get 10 power minus 12, right? So again, now if you calculate the pH, you get that as 12. So this is what we get from here, that from 7 to 14, this is constant. So just make sure you understand this calculation. Otherwise, it's always given in your book if you don't understand this properly, right? Like to how to calculate. If you're given the OH minus concentration, then calculate the pH. If you're given the H plus concentration directly, then it's a one-step thing. If it's you are given the OH minus, then it's a two-step thing, right? First you find the H plus and then use the formula, right? And always you need to remember that OH minus into H plus is always constant. Okay. So now that you understand this, this is you can understand it from here. This is exactly what we are talking about. Okay. Next thing is what we call the concept of a Ka, which is called the acid dissociation constant. So, so this is the concept that exists for weak acids or bases. So weak acids means that it is not up to like So this is 7, which is neutral. So we only go up till say maybe 3 or 4 here, and then higher is like 10 or 11, right? Like not so HCl, H2SO4, H2SO4, HNO3, whichever are the strong acids lie outside this region. So we are talking about weaker acids, things like acetic acid, CH3COH, or like this is basically weak acid, right? Like anything else, some organic acids, other organic acids are weak, maybe phenol, right? Like alcohols are weak acids, right? Somewhere, sometimes. Anyway, that does not matter. Uh, so like, so let's take an example of acetic acid here or vinegar, right? Or ethanoic acid, right? So CH3CO minus, right, which is the conjugate base, right, and then an H plus, right. So again, because it's a weak acid, so it does not go through what we call complete dissociation. So it goes through what we call partial dissociation. So in the sense, this acid, it is supposed to give H plus, right, but it does not give completely. So what it does is it kind of gives a little bit, and then it remains in its own form, which is in this own form, right? Like this is in water, and this is in water, and this is in water, right? But this does not split fully. Like this is as different to HCl, where it fully dissociates to give H plus and Cl minus, right? So this is what we this forms an equilibrium. It like maybe if you put say 100 of this 100 molecules, then maybe 70 of them dissociate, and then 30 may not dissociate. 30 just remain in its intact form, right? Okay. So once you understand that, then that means you can write the equilibrium constant, right? Or in this case, we call it Ka, not Kc. Again, similar thing, right? This thing, and then COOH. Now this time the denominator is not a constant, so so we don't kind of take it out. So we keep it like as it is. So this is what we call the acid dissociation constant. So corresponding to this, again, if you know all the three concentrations, then you can find that. Make sure you understand that if there are, like, say, some constants, like say maybe there was a 2 here and a 1 here as balancing constant, then they become as squares, right? Squares and cubes or whatever, right? Like X, Y, Z. Make sure you understand that. Um, okay, like how we found pH, that we can also find pKa, which is, and p always refers to minus log base 10 whatever of whatever, so in this case it will be Ka, right? So as opposed to pH, where you only needed concentration of H, right, here you will need three concentrations, right, to find this number out first, and then you can find the pK. Like pK is just, again, is just a number representation of whatever we are finding. Like imagine, like it can be difficult to say 10 power minus 14 every time, right? So we just say 14 or 11 or 10 or 11.2 or 10.3 or 2.4, whatever, right? That's much easier to say rather than 10 to the power of minus 3.2, something like that. So which is why we have this concept of pK just for convenience, or pH, right? Okay, so this is the acid dissociation constant. Make sure you understand what is happening here. Uh, so of course, so one thing that we can understand from here is the if p if K value is high, right? So that means these two are high, right? So if K is high, that means this is high and this must be low. In that case, these are high, right? And this is low. So you can see that the reaction has moved to the right a lot, right? So that means dissociation is good. That means it's a strong acid. So this generally means that it is a strong acid, right? Like how is this high, right? Like just follow this logic slowly. Feel free to rewind the video if you don't understand anything. So this is what they talk about here. Like equilibrium lies to the right. That means the acid is completely ionized, right? So in this case, what they did was they added these many No, this is an example. Make sure you read the book. Like you will follow things slowly, you will get it. Like I'm just skipping things a little bit here. Again, do the in chapter exercise as well. Uh, in this case, what are they talking about here? So they took a acid, a monobasic acid. So the idea about a monobasic. So let's cover that as well. So you can have either a monobasic acid like HCl, CS3COH, right? All these we call monobasic acid. I know that term can be confusing, but it just means monobasic means that it has one H plus to give, right? Which is as opposed to H2SO4, right? Which is called dibasic acid, right? Like because it has two H plus to give per molecule of the acid. Again, an extreme example would be S3PO4, which is like a tribasic acid, right? So it has three H plus to give per this thing. So in this case, they took an example of HA, which is a monobasic acid. A can be any anion. So in this case, it is Cl minus. In this case, it is CSCO minus, whatever. Or if it is HNO3, then it is NO3 minus. So whatever it is. So if it's weak monobasic acid, then in that case it splits as H plus and A minus, right? When an equilibrium sort of reaction. So you can write the Ka of this monobasic acid as H plus, A minus, and Ha at the bottom, right? Like so, with some basic stuff basically. Uh, if you know that there is only single source of H plus and single source of A minus, which is through this reaction, and there's no external thing that's interfering. In that case, both will be same. So H plus and A minus becomes same because concentration is same. Again, remember what concentration is. Concentration is always written as moles per dm cube or moles per liter. And dm cube and liter are same unit. 1 dm cube is 1 liter. So always remember this conversion. It is very important. Uh, so how many moles of a thing? So it can be 1 mole per dm cube, right? Or 1 mole per liter, right? Or it can be 2 moles per dm cube. Right? How many moles of a thing is per 1 liter of water? That's what we call concentration. In this case, yeah, so this is what is the unit of this thing. Always make sure that you understand the units properly. K can sometimes have weird units. Every reaction has a different K unit. So in this case, this is moles per dm cube. This is moles per dm cube. This is moles per dm cube, right? Like so, if you calculate the unit of this thing, will come out to be moles per dm cube per liter, right? If you calculate it for dibasic acid will have a square here, right? And maybe a square somewhere else, right? Like so, then in that case, you have to be careful. So this becomes a square and stuff like that. There are questions in your book about this. Make sure you kind of attend to that as well. Okay. So this is what they're talking about. Make sure you understand do the question slowly. Like they're telling you to calculate the value of K given that pH is already given. So if pH is given, that means H concentration is given. So you can figure that out, right? Whatever in moles per dm cube. And once you have figured out H concentration, you know that because there is only one thing present, which is methanoic acid, so it breaks off in a way that H plus and OS minus will have, or A minus will have same concentration, right? Because the source of A minus and the source of H plus is same, and they are produced in the ratio 1 is to 1, right? So if H plus has some concentration, then A minus will also have the same concentration. In that case, like this H plus A minus can be written as just as H plus square, right? Make sure like you understand how this is happening. So this becomes a square, and the denominator is just like what. So this is what you started with, as so these many moles you added initially, right? Of the starting thing. So from this you can figure out K, right? Similarly, a thing if you are already given K, then how to figure out pH, right? So that part is also given. So that both the things are important. How to go from K to pH and pK to pH. Again, these are very common popular questions. You need to understand this. Okay. So if you understand this, then the next thing that you need to understand is what we call a buffer solution. Okay, so let's talk about what a buffer solution is. So the property of buffer solution is it resists change of pH. So imagine if you have a beaker, right, of something, and which has say a pH of uh, say 6, which is close to maybe 7, but a little bit acidic, maybe something like blood, right? Blood has a little bit acidic pH, or a little bit basic, I think, but does not matter. It's very close to 7. In this, you add some strong HCl, right? So of course, you will quickly see that this drops very quickly to 4, 3, like maybe even lower, right? 2 point something, very quickly. Right? As soon as you have even 5 drops or 2 drops, it will immediately drop. So the idea is we want to have, say, a buffer solution here. Like the idea is replace this with something which resists change of US. So it's like, oh, instead of 6 drops, maybe you need to add now 10, 20 drops. Only then you see a corresponding that should. So make sure you understand that the change will still happen, but just will happen very late. So you want to resist this change. So this is kind of like a magic portion. Like, so idea is how do you generate such a thing, right? So the recipe for this is you mix a weak acid with the corresponding conjugate base, right? Or you add a weak base with the conjugate acid. Like in the sense, have two things in that solution. One is the weak base, and one is a conjugate acid of that base, or the other way. So one of the examples they have given is of acetic acid. So in case of acetic acid, right, which is example one here. So you add acetic acid in this beaker, but you also add a salt of an acetic acid. They don't react with each other because they are like there's nothing to react. One anion is same, right? Like this is a minus, right? But now understand what is happening because this is a salt and this is an acid and this is a weak acid, right? So weak acid part checks out, right? The second part is the corresponding conjugate base part, right? So this is the conjugate base. So now you might ask me, how is this a conjugate base? So because this is a salt always completely dissociates. So this is an ionic salt, right? So if you remember last chapter, ionic salt is just basically an anion and a cation, but always separately. They are always dissociated, right? Like we saw last time, right? Like if they are aqueous form, uh, they can be either be sitting at one corner, right? But if they are inside the liquid, that means they are dissolved. They will go off as two free ions, so CH3CO minus and Na plus, like that. So in a way, this separates out into two, and you have this and this. So this, so if this is the corresponding acid, then this is the conjugate base of this acid, right? So which is why this satisfies this criteria of a weak acid and the conjugate base of that weak acid. So this is the acid, and then this is the base of that acid. So just make sure you understand this, how this is formed. An example. So this is one solution, right? So an acid and a salt of that acid, basically, right? Another example of this one would be, I think they've given NH4OH, and yeah, let's just see the example that they've given. Yeah, like understand they have given how rainwater also forms a buffer solution because there is CO2, which is a conjugate base in the liquid, and that CO2 mixes with water to form carbonic acid, or which is H2CO3 or HCO3, right? Which is like kind of like a derivative of this. And this H2CO3 is as an acid, and if you remove one, right, like CO2 or HCO3, it becomes a conjugate base, right? And both of these kind of form a buffer solution. So this, which is why rainwater has like a constant acidic pH, which is of this thing, which doesn't really change that much over the years, except that when this balance is disturbed, in which maybe if you send too much of carbon dioxide, So that disturbs the pH a little bit. But pure rainwater in a way is a buffer solution. So make sure you understand this as well. And this is the example for the base side solution. They're saying if you have ammonia, right, and say some ammonium salt, right. So if you think about this, this is salt, so this will dissociate. So this is the corresponding conjugate acid now, and this is a base. How is this a base? Because base is anything that can accept H plus, right? So here clearly it is accepting H plus to become that. So again, we are adding two things, which is ammonia and ammonium salt. So these two together can form a buffer solution. These two together can form buffer solution, and they are just two examples of buffer solution, right? So make sure you understand this as well, because these are just important concepts, right? To go through every line, right? Like they kind of explain you things slowly a little bit, and they explain you why such a solution acts like a buffer solution, right? So let's go through that as well. So so you know that like how does a buffer solution work, right? So you start with an acid, right? So it of course it can dissociate, and it is in always an equilibrium, right? And that equilibrium is regulated by a constant Ka value, which is determined by the properties of the acid, and that Ka value will be given like this, right? So you can, in your experiments, these value, the right hand side changes, right? But this is always a constant for an acid, which is why it's called the acid dissociation constant, right? Like this is always constant, and the right hand side is what changes. So in your solution, right, you have something. So see, this thing can be produced from this thing, right? From through one thing, through this reaction. But you also have an acetic acid salt, CS3CONa, right? In that case, so that is so CS3CONa produces this guy. It can also be produced from the acid, but it disturbs the equilibrium, right? Like in the sense there is an external source that controls this and an external, like an input that controls this. So this thing concentration is determined from the salt, and this concentration is determined from input acid solution, right? So this is a constant as in you can control from outside. This is a constant, something you can control from outside, and this is just in general a constant, right? So if everything in the equation is constant, so this becomes in a way a constant or close to a constant, right? So if H plus is constant, that means pH of that thing is constant, which is essentially what we want, right? So the idea is, because this is externally controlled, this is externally controlled. Uh, this is basically a constant. So now let's try to understand it in different scenarios. So scenario one, say you add an acid to this acid in a buffer solution, right? So the idea if you add acid to a buffer solution, acid gives H plus. So what it can do is, say you have so much salt, right? You have so much of this that a little bit of the salt can come in and just kind of consume that extra H pluses that are coming from outside, so as to not disturb this equilibrium. Like keep this constant, right? And this is always a constant. So so a corresponding H plus is constant. So the extra H pluses that the acid is bringing, your buffer consumes those H pluses. So the salt ka CH3CO minus use up the H plus that is happening. Ignore the handwriting, but like the idea is salts, like salt is giving this part, right? So this uses up that extra H plus, right? Because this needs H plus, and there is a lot of the salt inside the solution, right? Now similarly, if you have a base in a buffer solution, now instead of the salt, the acids, which is the acidic this thing, right? It can form salt and water, right? And which is like the own reaction. So imagine, like, there's a lot of undissociated acid, right now in the solution as well. There is a lot of salt and a lot of acid, the two things externally. So if you add anything, then like that external stimulus just gets used up. So as a result, this equation की वजह से H plus का concentration remains the same, right? Again, this is the part that can be, I guess, a little bit confusing. So make sure you kind of understand this slowly and properly. Okay, again, go through your book for like exact wordings and clarifications, but this is the core idea of the thing. Okay. So there is this buffer related again, like K, we just saw that there is H plus A minus by HA, right? So we can take a minus log H here, minus log K here, which we call pKa, right? Minus log base 10 again. So again, you can write this as minus log base H and minus log base A minus by this thing. Again, you can also separate those two out, but I'm just writing it like this. A minus mod. Yeah, right. So this one becomes pKa. Sorry, my handwriting is really bad today. And this pH plus. Now, if I'm writing plus, then you can flip the signs there, right? So you get something like this. So this is the concentration of uh, acid on the top by this comes from the salt, right? As we talked about. So concentration of acid by concentration of salt. So this then becomes in a way like the equation that you can use. So if you know the K and you know these, like if you know three, then you can find the fourth one, right? Always. So this is what it is talking about. So they have kind of taken pH because pH is what we generally need to find. So if you take it to the other side, then it becomes salt by acid correspondingly. Like if you feel like you want to remember, then you can remember, but otherwise you can derive it also. It's a simple, like this is always given from the equation, and then you just have to kind of take minus log 10 on both sides. Right? There are some questions given here. Make sure you understand and do them. Again, questions doing, equilibrium question doing is the most important part because that is where your doubts will come and that is how you'll understand. I'll read this, I'll let this part be for you to read through. Again, this is a small section, but the idea is how where are buffer solutions used, right? Like in hemoglobin, your blood is a, as you talked about, hydrogen carbonate in rain is a buffer solution. Blood may hemoglobin acts like a buffer solution. And then this hydrogen phosphate, dihydrogen phosphate and hydrogen phosphate can also act like a buffer solution because they're conjugate base, right? Like this is an acid, and if you remove one H plus, then whatever is left is a conjugate base. So this is the conjugate base, this is the acid. So if you have a solution of both of them, then you form a buffer solution. So similarly here, hemoglobin and plasma proteins form a buffer solution. Again, if you want to maintain a constant pH, then a buffer solution is what you go for. In body, internal to the body, maintaining constant pH is very important because a lot of bodily functions depend on there being a constant pH inside the body. So this is something that we do. This is something that's important. Okay. Now from here it's a new topic. Let's just take a little bit of a small break. Like stretch a little bit, pause the video, and then we'll continue with the next one. Okay. Uh, so let's talk about the next topic now. So there are two more topics at the end. So one is called solubility, and so till now what we discussed was buffer solutions, right? And buffer solutions, to build up to the concept of buffer solution, we need to understand what conjugate bases, conjugate acids, concept of pKa, concepts of pHs, right? Once you understand all of that, then you can understand what a buffer solution is, which is very useful as a concept. Okay. Once you understand that, the next topic we need to understand is what we call solubility, right? So solubility is what we define like this, right? Solubility is basically the amount, right? In chemistry, amount is always number of moles. that you can dissolve in, right? So dissolve in 100 grams of water, right? Like, so that is what we say. If you take 100 grams of water, or 1 kg of water, some basically fixed quantity of water, then how much ever grams, number of grams or number of moles that you can dissolve. So, or dissolve, or like, so they also call saturate. So saturate, the idea is that you can, once you dissolve that much, there is nothing more that you can dissolve, right? So imagine that if, say, you have 100 grams of water and you're trying to add salt to it, right? You add a little bit of salt, um, and then you start stirring, right? So salt dissolves, right? You add a little bit more of salt, then you stir, then the salt dissolves. At some point, you can understand or imagine, right? Like that, after some point, it will stop dissolving. When it stops dissolving, then that is when you call the solution as saturated. So the solubility can be defined as till what point can you continue to dissolve, and after that it's saturates, right? So that is the idea. So you have numbers for everything. In sodium chloride, which is normal salt, you can dissolve about 36 grams before in 100 grams of water, right? For lead chloride, it is less soluble. You can only dissolve 1 gram. So solubility can be defined like this, right? Uh, okay. So solubility product is this thing. So the idea of a solubility product is kind of what we little bit talked about. That at the so whenever you add a salt, right? Like first, say AgCl or NaCl, right? Like they are first stuck in a lattice form, right? They are solids, right? The idea is solid, matlab, like both of them are in lattice form. That's something that we talked about in last chapter, right? As soon as you dissolve them in water, due to the hydrogen bonding, right? As you saw, right? The lattice, if there are positive H plus, whatever, in this case Na plus or Ag plus, whichever, the positive answer is there, then O kind of with the bent this thing, because of the polar thing, it has a delta minus, right? This delta minus kind of pulls it out and reduces its dependence on the internal Cl minus atoms that are connected here, right? So it kind of pulls it out. So because of which it becomes a free Ag in an aqueous form, and then slowly by the same process, Cl can also come out later, right? And similarly here, Na can come in aqueous form and Cl can come in aqueous form here. So this is what we call again solution or dissolving, right? Like as we talked about in last chapter. So in for this reaction again, what can happen is when you're close to saturation, then there are a lot of these ions in the solution now, right? Like all of them have kind of come out of this thing, and there's so many, like you can imagine that they start to recrystallize and form a bunch of salt again, right, in some other corner, because there's so many AgNCl inside the this thing that they might want to recombine instead of combining with H2O. They might want to combine with themselves again. So which is what forms an equilibrium. So Ag and Cl are recombining to form this, and this at the same time is going to form Ag and Cl. So like both the factors are there, and dynamic equilibrium can be achieved. So in that case, whenever there is equilibrium, you can always write K of that equilibrium. And in this case, we write it as KSP, or solubility product, or solubility, right? So this can be written as Ag plus Cl minus. Now both are aqueous form, so we write concentration of aqueous thing. We don't write concentration of a solid thing, right? We're just a lattice thing. So we just write something like this. So like we do the same thing as we did for ionic product Kw, where we take this thing and merge it into Kc, and we will just forget about everything. So we get what we call KSP. Again, this is something that is a property of the salt, right? And like how K is the property of an acid, this is a property of salt. So when I say property, it means it is constant for a salt. So if I give you NaCl, I can tell you the number of KSP. Like I don't have to tell you how much I took, or what is the concentration of NaCl, or how much whatever, right? Doesn't matter. The idea is I've just taken a salt, and that has some natural KSP. So that's the idea of a solubility product, right? This is what they talk about here. So make sure you understand this. Again, you can have 2's and 3's if there is equation something like this, right? So make sure you understand that. You need to know how to derive units. As I said, every k in every is equation dependent. So if this is the equation, then the k units are this, like not for maybe that equation, but for this equation k units will be different. For this equation units will be different. So make sure you understand that. Okay, so uh, so one thing that we are understanding from here, like how we saw in Ka, right? Like the higher the K, higher the acidity, because KSP is like all the ion concentrations are here, right? Like say Cl minus and Na plus, right? So the higher the KSP, we can say higher is the solubility, right? Like that's because that is the soluble part and that is the insoluble part on the left hand side, right? So that's one thing that we observe. So you can look at the KSP number between all of these. You can say that, oh, this is maybe a little bit high, right? Like this is very low, so this is probably not soluble. So, and you know that hydroxides are usually not soluble as salts because they form precipitate, right? Like we'll see it in the last chapters. Again, so there'll be few examples here. Make sure you do the examples. I'm not going through the examples. And the last thing is predicting precipitation. So if there is something that you can add, like say you're adding barium chloride and sodium carbonate into a beaker, right? Like barium chloride is one salt, and this is barium chloride will have some concentration of barium and chloride. The other one will have some concentration of sodium and carbonate, right? For BaCO3 to BaCO3 to set to precipitate, right? There must be enough concentration above the KSP. So the idea is barium concentration comes from barium chloride, CO3 concentration comes from sodium carbonate, and because this number is higher than whatever the KSP is, sorry, if this number is higher than the KSP, which is this guy, then a precipitate will form, otherwise it will not form. So it is a kind of, you can predict if there will be a precipitate or not. So these are useful things. Uh, Again, there's something, a very important idea is called the common ion effect. So the idea is if say there is a reaction, right, like Ag and Cl, right? If you say add now, like say there is a very small amount of AgCl present, right? And so Ag might not form a precipitate because there is like Ag concentration is less, Cl concentration is less. So it might be lower than KSP. So even though there is AgCl present, which is an insoluble salt, you don't see a precipitate. So the idea is you add, like say, another source of sodium chloride, right? Just add sodium chloride to this. Then you will artificially increase the concentration of this. Now, this will push the KSP value, like the product, right, of this and this up because one of the terms has risen. Because this has risen, this whole thing will now be more than KSP and you will see a precipitate of AgCl now. Even though there is, so this can be used to detect small presence of Ag inside this thing, right? So this is what we call the common ion effect. Like even though you were not supposed to see the precipitate here, because you artificially increased the Cl minus concentration through a common ion between AgCl and NaCl, right? That increased the Cl minus concentration. So the product increased, product of concentration, and that became above KSP. And when it is above KSP, then as you saw earlier, a precipitate will form. Right? Make sure you go through this explanation again and understand this. Once you do that, then you can use it to detect small quantities of Ag plus. So that is the idea. So this is a very useful technique again. So two useful techniques we kind of understood today. One is common ion effect and one is buffer solutions, right? So this is the main idea here. So then chemistry, we need to understand these core ideas on which they do experiments. Right? So make sure you kind of naturalize these things. Okay. And the last thing that we need to understand in this chapter is called partition coefficient. So let's understand this as well. So partition coefficient again. So this is the diagram of partition coefficient. So make sure you understand this. Uh, so what is happening in partition coefficient? Again, remember this is equilibrium chapter. You are always searching for equilibrium. So what is happening here is uh, there is an organic solvent, okay, which is say some solvent, right? Maybe called ether, maybe some ether, right? And then the lower one is water. So these are two solvents, and they are what we call immiscible, right? So that means they don't dissolve with each other, like they sit like oil and water, basically, right? Now inside this you have NH3 say which is dissolved, right? So what you'll see is NH3 can get dissolved a little bit in water, right, and a little bit in the organic solvent. So this is depending. So organic solvents usually are non-polar, right? And this water, as you know from the last chapter and today's discussion, that water is polar, right? Like O minus and bent, so delta minus and delta plus. So because of this O minus, it dissolves the polar molecule. So if there's NaCl, then it pulls Na here and Cl minus, right? But non-polar things, if this is already non-polar, if it's a covalent thing, then it won't dissolve in a polar solvent. So polar solvent dissolve certain things and non-polar solvents dissolve other things, right? So if say in the case of ammonia, depending on if it has this thing, so it does ammonia have a net dipole moment? So if you think about it, ammonia shape is like there is five here and then three hydrogen bonds are arranged like a tripod, right? So it will have a net dipole moment. Because it will have a net dipole moment, it will like to dissolve itself in water, which is a polar solvent. And but there will be some quantity that will dissolve in organic solvent as well, right? So what happens is, so there is some quantity that is present here of ammonia, right, and some lesser quantity that's present here. Now what happens is in an equilibrium, like so this NH3 from the organic solvent, right, or the non-polar solvent can go and kind of into the aqueous form or the water form, right, and then it can happen the other way. So this is what we have, like an equilibrium, like a transformation from this to this and that to this, right? So we can again write a K partition coefficient for this sort of reaction. So which can be like NS3 in aqueous form and then NS3 in the organic solvent form, right? So this is what kind of like concentration there and concentration there. Again, so this partition coefficient is also a constant between two certain things for a particular material. So if for NS3 between say ether and water, it will be some constant. So this is something that you can look at. So this is what is called a partition coefficient. Attempt this question, you'll get a hang of it. And yeah, so solubility of that solute, it's called a solute. So relative solubility is what determines this value of Kc, right? As we talked about. So again, it is dependent on that polarity of thing. So iodine, which is say a molecule, it will not dissolve very well in water because iodine itself is non-polar, right? It is because II it's symmetric, so it kind of cancels each other out, the dipole moment. So it dissolves well in this thing. So in cyclohexane is the organic compound and organic solvent, organic compound and an organic solvent. So it will be non-polar. So it will dissolve iodine nicely, but water will not dissolve iodine very nicely. There is some exception here, like make sure you understand this, but the idea is this core idea here. Again, so you can understand things like this, and this is the main idea. And the last topic that they talk about is how this is used in chromatography. So the idea is there is in chromatography there is a solid or what you call the stationary phase, right? And top of this is what you call the mobile phase, right? So the idea is the mobile phase is kind of constantly moving. So now if you have say a thing or a solute that dissolves well in the mobile phase. Now because the mobile phase is moving, say it is water, right? And say you're running a jet of water over a stationary solvent, then whatever needs to dissolve in the water in the upper thing more, in the mobile phase more, it will just get dissolved there and get carried away. So this can be used to do what we call chromatography or to separate things out. So if say some things are more easily soluble in the stationary phase, then they will just stay stuck. Even though there is water going on the top, they will not move with the water because they like to be dissolved in the lower stationary phase. But if say something likes to be dissolved in the water phase or the mobile phase, then they can just like get themselves dissolved in the upper one, and then just the water will carry them forward. So this can be used to separate things which are water soluble and say like mobile phase soluble and stationary phase soluble. So that is the idea behind chromatography, right? So if we quickly look at maybe a picture, paper chromatography, like right, we see something like this. So things kind of start moving. So you must have done this experiment in lab also. So you see that uh, a dot of different color can move this different amount, right? This depends on how much solubility it has in the mobile phase. So you can separate out say blue color from yellow color. If you have a solution of first and second, then you can have two different blobs. So you can know that the original solution contained two things. So this is the idea, right? Like so this drop that you put here uh, contained one, two, three, four things, right? This drop contained three things. So this is how you can know the constituents of a drop or constituents of whatever you are looking at an unknown thing, right? Yeah, just understand. Yeah, again, you'll understand better when you go through things yourself. Do the questions. Equilibrium or and general physical chemistry is all about doing questions. Read the book and let me know if you have questions. We'll stop here.